live! Hi folks, and welcome to our tutorial on reverse engineering with IDA. No steps skipped. We show you all the gritty details. So with that, let's get started. For today, we are only going to be using IDA. And if you don't have a copy of IDA Pro, which I'll be using, you can work along at home with a copy of IDA Free. All of the features and functionality that we work through in this series, you can do with the free version of IDA. None of the techniques that we show you in this series are going to be limited by the free version. So let's open up IDA here, and I'm going to open our binary. So I'm just going to click open, and it's called stage 1. Now, I'm going to just use the default IDA settings. So I'm going to click OK, and I'm going to let it do its thing. Now, if you're following along at home, I've linked the binary below. There's a hash, and you'll also be able to download it from UnpackMe. The way this series works is hopefully you're either watching the tutorials and then doing the exercises afterwards, or you can actually watch and do the same reverse engineering that I'm doing on screen at home. I'd encourage you to do it that way so you can stop the tutorial and sort of work through the controls yourself at home. Because some of these videos will be longer, it's probably easier to actually do it as you watch rather than doing it after you've watched. Okay, so now we have the binary loaded up in IDA. This is our typical entry into IDA. I'm going to press the spacebar to switch our view into linear view. If you hear some noise in the background, it's just the dog. He's sleeping beside me. Most of you are probably familiar with Boris. Okay, so I've pressed spacebar, we're in linear view, and I just want to point out two things that I usually check before we get into the actual analysis here. I like to go to the exports, and generally this just tells me what kind of binary I'm looking at. If it's an exe, there's usually a start function here, which I'll show you in a later video, but that generally indicates that it's an exe, and that's the entry point of the exe. In this case, as I mentioned, it's a DLL, and we have the DLL entry point, which is common to all DLLs, and there's one export, ordinal one, called work. Now, before we dive in and start looking at these functions, I'm just going to pop over to the imports, which is the other tab that I usually take a gander at before I start analysis. This just tells me all of the functions, all the APIs that have been imported into the binary statically at compile time. Obviously, malware makes heavy use of dynamic import resolution, so this doesn't often tell you too much, but it's a good first glance, and we can see here there's a bunch of stuff with kernel 32, and we see one shell execute ex function from shell 32. That's pretty interesting, as that is how you launch an executable. So this might be an interesting API to look at later on if we get stuck. Let's go back to our exports here, and we'll begin our analysis. We'll jump into the DLL entry point. Now, normally there's not supposed to be a lot of code in the DLL entry point. The DLL entry point is used to set up the DLL before any of the exports are executed. Sometimes malware developers will hide code in the DllMain, which is why we're going to take a look at it. But I did see that other export work, which sounds very interesting. So we'll take a look at that second. But first, let's take a look at DllMain here. And what I'm going to do, just because this tutorial series really is trying to give you no steps skipped look at reversing with IDA, I am actually going to walk through the DllMain with you. Okay, so for our analysis here, I'm going to mainly use the pseudocode. So I'm going to press F5 here, and that is going to show me the pseudocode. Now, there's different approaches to reverse engineering. There are many people who I respect and who are excellent reverse engineers who only do the reversing of the disassembly. All the power to them. My approach is to use the pseudocode as often as possible and to only use disassembly when I believe there's some sort of problem with the pseudocode, or to double check things that just can't be decompiled properly. So for the majority of the tutorial, we're going to be in the pseudocode. I am going to set this up with a split view, so I'm just going to pull the pseudocode down and dock it. But what I'm going to do is I'm going to mostly minimize this disassembly here. So we're mostly going to be looking at the pseudocode. I'm also going to shift the function window over here to give us a bit more room for the pseudocode. The main focus of the reversing will be the pseudocode, and then we'll fall back to the disassembly if there's some sort of problem. Now, one last thing before I forget, I will right-click and synchronize with the disassembly view, just in case we have to hop back and forth between the two. We just synchronize them up. Okay, so now we're in the entry point here. I've been calling this DLLMain, but actually the entry point has some setup code before it actually calls DLLMain. And I want to go through that with you guys here. Again, I'll only do this once, but it's worth doing it once just so you understand what's going on here. Now, before we go through this, it's probably worth pulling up the MSDN documentation for DLLMain. One of the nice things about Windows is almost everything is super well documented. So you can oftentimes take the documentation and match it to the pseudocode that you're looking at. So why don't we pull that up right now? Okay, so we now have the MSDN documentation for the DLLMain entry point. I will link this below if you guys want to give it a closer look. But really what I want to do is I just want to show you the arguments here. Dog was snoring. The main advantage of the documentation is it'll explain what these arguments actually are, and it'll give you a better understanding of what you're looking at in the pseudocode. So we can see here that H instance is a handle to the actual DLL. FDW is the reason for calling the function. And the LPV reserved is a reserved argument. Now to start out with here, let's take a look at this FDW reason. You can see here that this is actually checked in a case statement here to determine why the DLL was called. And there's a bunch of different reasons why the entry point or DLLMain might be called. Of course, the most common one would be DLL process attach, which would be the first time that the DLL is loaded into memory of a process. So that's probably the most common one. We have a thread attach, thread detach, and process detach, which is obviously part of the cleanup or when the DLL is being shut down. So that's basically the FDW reason. Let's pop back to IDA and see if we can't annotate the pseudocode a little bit with this in mind. Okay, so we're back here. We have the arguments. They look like exactly what we saw in the documentation, and we have this FDW reason here. Now we can see FDW reason is checked against the constant 1. Now we know in the documentation that the FDW reason is actually checked against a bunch of constants which have names. Now what we need to do in IDA is we need to associate the name with the constant that we see in IDA. So we can see here it's 1. We have to figure out which one of those constants is 1. And this is where we're first introduced to enum in IDA. If we select the constant here and we press M, it's going to pull up a dialog box saying it doesn't actually have any constants associated with 1 yet. Of course, we haven't loaded any, so that's to be understood. It says, do you want to search for them in standard enums? We're going to click yes, and this is going to bring up a little search box here. Now, inside the search box here, we have access to all kinds of names which are associated with the constant 1. What we need to do as reverse engineers is we need to choose the right one. So if we go back and look at the documentation quickly, we can see that all of these constants begin with DLL underscore something. So let's go back to our enum and let's type in DLL underscore, and we can see here there's only one DLL process attach. That makes sense. And so we're going to select OK, and it's going to now apply the label here to that constant. This is a perfect example of IDA displaying my understanding of the binary. We could have chosen any constant we wanted. So if we press M again, go to new to add a new one, we could have chosen any one of these and it would have been incorrect. We would have made this code look silly to anybody who understood what was going on. But IDA wouldn't have stopped us from doing it. Let's not actually do that. We'll cancel this out. But IDA wouldn't have stopped us from setting any label we want on that constant. That's one of the things about this process, is that it's really up to us to choose the right documentation for the code. IDA is not really going to complain unless we do something really crazy. So that's just something to keep in mind when you're applying these enums. It's always good practice to figure out where they're documented in MSDN and see, does it actually make sense what I'm applying here? And now a word from our sponsors, us.
What's up? Johnny Sins here. I just want to clear something up. I am definitely not Sergey without glasses. Although, am I?
Hey folks, just because I'm not Johnny Sins doesn't mean I'm not getting busy on camera all the time. I'm so busy, in fact, that I've created a huge catalog of video content on Patreon, which if you like these streams, you should go check out. We have over 140 hours of streams, live streams covering everything from deobfuscation, building config extractors, unpacking malware, everything you could think of related to reverse engineering malware. We also have in-depth tutorials covering things like unpacking VM Protect, how to set up a malware analysis lab, how to build a config extractor, calling conventions, what that means.
What the hell is even that?
All kinds of in-depth reverse engineering content on OA Labs Patreon. Go check it out. We'll see you there. So in this case, we're checking to see whether the reason is DLL process attach, which we know indicates this is the first time the module has been loaded into a process. And if it is, we're going to call security init cookie. And regardless of what it is, we're also going to call DllMain CRT startup. Now, I'm not going to go into reverse engineering the security cookie here. It's probably good to know about how this stuff works, but that's not going to be the goal of this tutorial series. But I will just mention that the security init cookie is a cookie that prevents buffer overflows. It's a security feature, an optional feature that's set by default. It can be turned off for some compilers. But in general, whether it's a PE file or a DLL, you'll often see the security cookie initialized as one of the very first things that's done in the code. You guys hear my dog walking around. He's upset about the security cookie. Okay, so that just leaves us with this second function, which is called regardless of the reason for attaching to the DLL, which is DllMain CRT startup, and we pass in H instance DLL. Let's double click on it and see what that has in store for us. Okay, did you notice something when I double clicked on it? Take a look at these arguments here. If you remember from just a minute ago, there was only one argument being passed in from the function that called this. The reason for this discrepancy is that IDA had not decompiled this function yet, so it actually didn't know how many arguments it took. It was just guessing that it took one argument. So what we're going to have to do is we're going to have to now go back, and you'll see now in this function, IDA now knows that this takes 3 arguments. Now this is extremely common, and you're going to see this all over the place when you're navigating pseudocode. If you navigate into functions which you haven't previously navigated into, oftentimes the arguments will change, and it's worthwhile going back and checking to make sure the arguments that come from the caller function are documented properly. Now, if you have IDA Pro, there is a trick where you can choose file, produce and produce C file, and that will force IDA to decompile the entire binary, thus fixing the arguments for every single function. I'm not going to do this because many of you are probably using IDA free, which does not have that feature. So you won't be able to do the same thing as me, and I want what I'm showing on the screen to be as close to what you're seeing at home as possible. So I'm going to do it the old-fashioned way, the same way that you have to do it at home, which is every time we navigate into a new function, we're going to check to see whether the arguments have changed. If they did change, we'll go back and fix them in the caller function. So we've come back to our caller function. We take 3 arguments, and the best practice is to mark the types for these arguments for this function now that we know what they are. Now, if you're not familiar with what that means, each function has a prototype. If we press Y, we select it and press Y, we're going to bring up the prototype for the function. Now, I'm going to copy this out into Sublime Text so you can see it a bit better. There you go. So right now, IDA thinks that the first argument is a void pointer, the second argument is a dword, and the third argument is H instance. And it knows that the H instance label is H instance DLL because it has figured that out from the caller function. However, if we look at the caller function, we actually know a bit more about this. We know the names of these two. So we know that the middle one here is FDW reason. And we know that the first one is LP reserved. We know the type of the first one is LP void. We know the type of the middle one is a dword. And the type of the last argument is H instance. And again, if you're unsure why we know that, it's because these arguments are actually the same exact arguments that were passed into the DLL entry point. They've just swapped the first and second one, but they're the same. So we know the type and the name of these arguments. Let's copy this out. I'll close up our Sublime here, and we'll paste it into the types, press OK, and IDA has now applied that to this function. Now you can see when I hover over it, all of the arguments have names and they have the correct types. And if I double click on this function, you'll see that we now have names for all the arguments and the correct types are set for all of the arguments. All right, so now let's take a look at what we're doing here. The first thing I like to do is what I call a freebie, which is to propagate all of the arguments, figure out the code based on their type and what we know that they do, and then go back and look at the code as a whole. So this is kind of a manual process where you're documenting the code based on what you understand about the arguments that are passed into the function. The place I'd like to start is with this FDW reason, because we know what this is. This is the reason for the DLL being called. And we also know all of the constants that it's compared against. So we can look through the code and see, oh, there we go, we're comparing against a constant. So now we can apply our enum to this constant here. So press M, and we know that this is the DLL process attach. Let's see where else it's compared. It's compared against a 2, so let's highlight that and press M. DLL thread attach. Where else is it called? Here it's compared against a 1. Here it's compared against a 3. All right, there we go. Now this code is looking a lot more readable. And we can also see that DllMain here is called, so we're finally at the actual entry point of the code that would be written by the developer of this DLL. So that's really what we're looking for. But let's just read through the CRT startup here to just get an idea of what's going on. So if the reason is not null and this dword is not set, we don't know what that dword is yet, or the reason is DLL process attach, or the reason is DLL thread attach, and CRT init fails, return 0. So inside the if statement, they're actually calling this function here, and if it fails, then they return 0. Now we can look at CRT init, but I'm not going to do the full reversing of this, mainly because we've talked about it in a previous tutorial, in fact 2 different tutorials if you want to go back and check those out, on C runtime initialization, and also because they don't have much bearing on what we're doing here today. One thing that might be kind of helpful is if you go through here and you can see, get command line is going to store like a pointer to the command line string in this global variable. Maybe you want to rename it. But again, we've sort of covered this before, so not much point going into it in depth. I will point out, if you are brand new to IDA and brand new to reverse engineering, this dword underscore in blue generally indicates that this value is a global. That means that it's actually stored inside the binary, not allocated dynamically at runtime. A way you can double check this is if you just double click on it. I'm going to scroll over so we can actually see the disassembly. You'll see when you double click on it, it will highlight in the disassembly where that address is in the binary. And we can see that this is actually in the data section of the binary. So that's what we mean by a global, and generally IDA will preface it with the D word or Q word or whatever size it is, underscore the actual address where it is in the binary. Again, I'm unsure of the level of everyone going into this series, so a lot of this might be very redundant and boring if you've used IDA before. I'm just going to try my best to explain some of these things that might be a bit new to some people who are using this for the first time. So if we want to rename that, the best way to do this is take a look at the function here, get command line A. Let's pull up the documentation for it. Documentation is going to be a big part of this tutorial series. All right, so we've pulled it up on MSDN, and we can see that this retrieves the command line string for the current process, not the DLL. Remember, this is a DLL. This is for the current process. and it returns an LPSTR, so we know the type that it returns. So if we go back to IDA, we can type and name that variable where the response is stored. So press Y to apply the type. Okay, and N to change the name. For globals, I like to preface them with G underscore, and then I'll just give it the name command line string, okay? And if we double click on it, you're gonna see now it's also labeled in the disassembly, in the memory slot where it exists in the data section. So that's just an example of naming a global. Again, if we find this used elsewhere in the program, we'd have to go back and label it. But for now, and because I've looked at this binary before, let's skip over this and we'll move forward with the rest of the CRT initialization routine. So let's go back, we'll give ourselves more room, and let's continue looking at our function here. So again, if it's DLL process attach or thread attach, we call CRT init, and we pass the H instance forward and reserved as arguments. If it fails, we return 0. Importantly, we return 0 and do not call DLLMain. So the CRT init has to complete successfully before we call DLLMain. However, if that does complete successfully, we don't jump into the if statement, and the next thing we do is call DLLMain. And of course, for DLLMain, let's press Y to check the types. All of the types should be set correctly because DLLMain is a known function, which is why IDA is actually able to automatically set the types and the name for it because it knows what it is. Now, before we dive into DLLMain, it's probably good to take a minute to talk about how IDA has these automatic types. If we go to View, Subviews, and Type Libraries, you're going to see this is where IDA has loaded its automatic types. Now, I don't know if automatic typing is the correct way to refer to this, but that's usually how I think of it. What these are is these are definitions of types. So these could be functions and variable types, as well as the enums that we were using earlier for the constants. All of that information is contained inside of these type libraries. When you load a binary, IDA will try to automatically determine what compiler type and version was used to compile the binary, and it will guess at loading the correct series of types. So in this case, it's guessed that the Microsoft SDK, so this is the standard development kit, i.e. all the libraries for Microsoft user space, it's going to load the types for those for Windows 7. Now, you might be wondering, what does this Windows 7 thing mean? What it means is it will have types for Windows 7 targets. So anything that's going to run on Windows 7, they're going to have the types for. So if you had something that was compiled for like Windows 11, then you'd want to run the Windows 11 types, something like that. Now, if we right click here and want to load a type library, you're going to see these are all the type libraries that IDA has available to it by default. Sometimes when you load a binary, IDA is going to have a hard time figuring out what the compiler is or what the version of the compiler is. So it's not going to load the right types, or maybe it's not going to load any types at all. This is especially the case for shellcode where there's no headers. So if you load shellcode, IDA has no clue what type libraries to load. So it's all up to you as the analyst to figure that out. Generally, the easiest way to do this is to use a service like UnpackMe, which will tell you all the compiler information, or you can use die, detected easy here, and you would just open the binary in die and look and see what compiler type and version was used. In this case, they think that it's probably Microsoft MSVC 2010. So we're probably okay with the Windows 7 types. It's probably fine. One of the things to keep in mind here is that Windows is super backwards compatible, so even if you kind of miss the version by a bit, you're usually okay. Famous last words, but usually you're okay. The main thing is just make sure that you get the SDK loaded if it's an MSVC binary, so if it's compiled with Visual Studio, and make sure you get 32 or 64-bit types loaded. Don't load 32-bit types for 64, obviously, right? One other thing to point out, which is not important now, but maybe later, is there's also this Windows native API, so the NDK, which has types for lower level structures, structures that you might see in the kernel, or even things that are referenced in userland but are not well documented or intended to be used by a userland developer. So sometimes if you see some structures, especially structs that are used to pass to syscalls or to DLL directly, it's worth actually loading these libraries. Now we don't have to deal with that today, but I'm just pointing that out to you. If you find that you're missing some types and the binary you're reversing makes use of DLL or syscalls, just load up the native API types and you should have that sorted out for you. So in this case, we can just cancel this out because IDA has correctly loaded the types for us. But I did just want to point that out for you. That's why you get this nice sort of markup where IDA knows what the types are for certain standard Windows functionality. All right, now just one more thing before we dive in here. If we take a look at our documentation for DllMain, we're also going to know what the return argument is. Here you can already see, if I hover over it, you can see it's a bool, a true or false. But let's pull up that documentation. So here we go. Let's scroll down to our arguments here. The return value, when the system calls the DllMain function with DLL process attach, the function returns true if it succeeds or false if the initialization fails, obviously 1 or 0, true or false. Let's go back to IDA now and we can mark up the rest of the code. So we know that this variable is the return from DllMain, and we know that this is init status, right? So this is the initialization status for the DLL. And now that we know that, we can figure out the rest of the code here. I'm also going to show you one other nice trick with IDA. You can see here that init status is assigned to v7, which is then returned. And you might be wondering, well, isn't v7 the same as init status? Why did it assign it to another variable if it's just going to return it? What's going on here? Well, if you hover over init status, you're going to see that it's actually a register EAX, and it's being moved into a local variable bool v7. Now, when it comes to the pseudocode, the higher level code, you don't actually need to know that. This is just a compiler thing where it's actually saving the register into a memory slot so it doesn't get killed by these other calls. But for the pseudocode, this looks kind of messy, and a way to clean this up would be to just go to the variable v7 here, press the equal sign, and it's going to say, do you want to map EAX to this variable? And if you click OK, it will just combine the two variables so you don't see that assignment, and now you only have one init status used everywhere in the program. Now, this makes the code look a lot cleaner, and it's super helpful if you're dealing with messy code where there's a lot of these like assignments. Just be careful, if you use this incorrectly, you'll clobber variables that you need for other parts of the code that you're reverse engineering. So only map the variables if you're absolutely sure that variable is only used once for the mapped variable. So if you know that, you can map them pressing the equal sign and selecting the register you want to map it to. Okay, so once we've done that, this code is a little bit cleaner. And we'll just finish the reverse engineering before we jump into DllMain here. We can see this if the reason for the DLL being called is process attach and the init status fails. So if it's not 1, then we're going to call DllMain again, but this time for the FDW reason, the central argument, we're going to pass 0. Now, again, we know all of the constants that FDW reason can be. So if we highlight that 0 and press M, we can now assign a constant to it, which is detach, which makes sense because this is the cleanup call to DllMain. So now our code is fully documented. We're going to call DllMain up here, just passing in directly the arguments that were passed into the DLL from the entry point. And if that fails, we're going to call DllMain again with process detach as the reason, which should trigger the cleanup code for the DLL. So now we can see the two different places where DllMain is called. Let's jump into DllMain and start reverse engineering the actual code.
My disappointment is immeasurable, and my day is ruined.
Well, isn't that a surprise? DllMain does nothing. Now remember I said most of the time DllMain is not going to serve much purpose. It's only real reasons to set up the environment for the other functions that the DLL provides. It's always worth looking at because sometimes malware developers will hide some code in there. But in this case, no code hidden, they just return true, and that's about it. A little bit anticlimactic. All right, let's go over and take a look at the only export from this DLL, the only function that you can call in this DLL other than DllMain, and hopefully that has some code in it. So let's go to our exports, we'll go to work, and now we have some code to actually reverse engineer. I hope you enjoyed that, and just a reminder that this is part 1 of a 12-part series that is available on Patreon. If you enjoy this kind of content, go check it out. The link is below. We'll see you there.